Hi again, everybody. Welcome back to MTED 110. Today we're going to be doing lecture 1A, and we're starting chapter 1, and we're going to be doing our first activity, our first activity, and we'll talk about that in just a minute. This lecture should actually be fairly short. I think it's only going to be about 20, maybe 30 minutes before the activity is introduced. So let's go ahead and get started. Okay, so chapter 1 is all about reasoning about quantities and problem solving. So let's start with reasoning about story problems. And the question that we're going to ask ourselves is, how can students approach a story problem? That's the question. How can they do it? Well, a 1988 study conducted by one of the authors found that students used one of the following 7 strategies when they were interviewed after solving a problem. 1, they would find the numbers in the problem and just do something to them, usually addition. Guess at the operation to be used, perhaps based on what they had just recently been studying. Let the numbers tell you what to do. So for example, one student said, if it's like 78 and maybe 54, then I'd probably either add or multiply. But if the numbers are 78 and 3, it looks like a division because of the size of the numbers. They would try all the operations and then choose the most reasonable answer. They would look for keywords to decide which operation to use. We're going to explore that in the activity, actually. The next activity, not this first one. For example, the words altogether can imply addition. 6, they would narrow the choices based on the expected size of the answer. Or 7, they would choose an operation based on understanding the problem. So, so once you read through these, one thing I want to point out is this. Only one of those methods actually involved understanding the problem. And that's the main idea here. If you look back at these, look at the structure of these strategies, right? 1, find the numbers and just do something to them. Do something to the numbers, right? Guess at the operation to be used based on what we've been studying. Oh, this has got to be division because we were just talking about division today, so this has to be a division problem. Let the numbers, quote unquote, tell you what to do. The size of the numbers indicate that, maybe they wouldn't give us a question this hard, so it's got to be division if it looks this way. Those kinds of strategies, right? Try all the operations and then choose the most reasonable answer. Look for keywords. Narrow the choices based on the expected size. But yeah, all of these previous ones, 1 through 6, they don't actually involve understanding the problem itself at all. They don't involve understanding the problem. Only one of them does, and that's part 7, where it literally says you choose an operation based on the understanding of the problem. So first of all, I want to say this: don't feel bad if you're like, "Oh, I've done that before," because we all have, and in fact, in standardized tests, you're encouraged to do that kind of thing, right? You're basically told, "Oh, narrow it down to 2 choices and then make a best guess," kind of thing, right? Those are like testing strategies. But the catch is this: those methods, 1 through 6, involve some degree of what I like to call gaming the system. What I really mean is that in those methods, the students have shifted their perspective and they are no longer trying to understand the problem and answer the question. What they're doing is they've recognized that they are in an assessment scenario and they're essentially trying to defeat the assessment, or in this case, like a test, right? So they recognize that they're being tested in a certain way and they stop trying to understand the problem, they start trying to defeat the test. That's exactly what's going on with these methods, right? So find the numbers and just do something to them. That's just like, a wish on the wind, essentially, right? Um, Guess at the operation based on what's been studied most recently. Sorry, one second. Too many things going on here. Delete. Delete. There we go. Guess the operation to be used based on what's been most recently studied. That's not actually understanding the problem. That's saying, okay, what context is this question being asked of me by the teacher? Okay, I'm being tested. We were just learning about division. This has got to be a division problem. We were just learning about it, right? That's not actually thinking about the problem and solving the problem. That's like taking this step back and realizing that you're in a testing scenario. So again, first of all, we've all used these methods before, so don't feel bad if you've done that yourself. And in fact, you're encouraged to do it on a lot of standardized tests because the point is to pass the test. But the truth is that Those approaches are all antithetical to the goal of education. Education is about gaining knowledge and deep understanding of things, and methods 1 through 6 do not do that for you. They don't do that at all. What they do is they basically just show that you know how to, worm your way through an assessment. But that's not actually knowledge, right? So when we're teaching and when we're learning, we need to be careful that we're not that we're not cheating ourselves out of our education. And using methods 1 through 6 is cheating us out of our own education, and your students will be cheating themselves out of their education. Um, uh, yeah, I'm sure you know what I mean. You know what I mean. If that doesn't make sense, I'll be happy to talk about it more. Or if you want to share your own stories, please do in the collaboration meeting because it's a fun discussion to have. Yeah, so those are antithetical to the goal of education. All right, so the book talks about this. So we'll go over it here. These are Polia's 4 steps for problem solving. So the first step is to understand the problem. How do you do that? Well, you ask yourself these questions. Ask yourself these questions. Is it clear to you what is to be found? What are you looking for? Do you understand the terminology used in the problem? And this is a good red flag. If you're trying to do a story problem and there's a word that you don't understand, you need to look up the definition of that word or make sense of what that word means, because if you don't, you're not going to have a deep understanding of what the problem is trying to ask. You're going to be halfway lost from the get-go. Is there enough information? Is there irrelevant information? Are there any restrictions or special cases to be considered? Essentially, understand the problem. For me, as a mathematician, I will spend an insane amount of time on this step. I'll reread the question 20 times. I'll reread it out loud. I'll rephrase it in my own language. I'll make my own words and try to say it again in my own words. These are all techniques that you can use to understand the problem, and I encourage you to do so. Second, you have to devise a plan. Essentially, come up with a strategy that you're going to use. How should the problem be approached? Does it appear similar to others that you've solved? Maybe those techniques would help here. What strategy could you use? So you devise a plan, and then once you have it, you carry out the plan. That's step 3, carry out the plan. But then there is step 4, which is possibly the most important step. It's when you look back. You look back. And when you look back, you're asking yourself, is your solution correct? And does it make sense in the context of the problem? This is a big one. So the idea is this: a lot of times you'll be doing a math problem, grinding away at it, you're getting really tired, and you're getting there, you get an answer, your calculations are done, and you're like, oh, done, and you dust your hands off, and then you walk away. Okay, so let's say the question is how much liquid is in this can, and your answer is 24 gallons. Well, uh, does that make sense in the context of the problem? No, that doesn't make any sense in the context of the problem, because this is just a standard 12-ounce soda can, right? So it makes no sense to say that it holds 24 gallons. It doesn't make sense in the context of the problem. But through the problem-solving process, you get wrapped up in it, and you just get so burned out by the end that once you get a result, you just want to spit the result out, dust your hands off, and walk away. We all get that. We all go through that, but that's going to mess you up. You have to look back and make sense, or ask yourself if your answer makes sense in the context of that problem. So those are Polia's 4 steps for problem solving. Here's some other strategies that you can use, just some general strategies. You can look for a pattern. You can examine a related problem and see if that could be applied here. You can examine a simpler case. You can make a table. You could identify a sub-goal. This is a big one too. A lot of times the problems that you're solving are pretty big in scope, and you can't just answer them right out. That's actually one of the first things that I tell my students when we're learning about story problems or word problems, is that you shouldn't feel like, and nobody expects you to be able to look at a problem, read this paragraph of text, and just get the answer right away. That's really not how it works. You should be sitting there and rereading the question a bunch of times and thinking about it, and so on and so on. Sometimes it helps to identify a smaller goal, like, okay, if I can figure this out, then I can apply it to this part of the problem, and if I figure this out, I can apply it to this part of the problem. That really, really helps. So try to identify a sub-goal. That helps me a lot, at least. You can write an equation. That's actually something you'll have to do in this activity, activity 1A. You can use guess and check. Guess and check is a problem-solving strategy. It's a valid method of solving a problem. It just may not be the most effective method. A lot of times, guess and check can leave you guessing and checking for the rest of your life. So you have to be discriminant with when you use the guess and check method. You can also work backward. Funny enough, sometimes knowing the answer that you're supposed to arrive at makes it easier to know how to begin, or it makes it easier. It makes it easier to know how to work toward the beginning than to go the other way. Like, you ever do those mazes on, when you go to a restaurant, they've got the little child's maze or whatever, and maybe you did some more complicated ones when you were older. Did you ever notice that sometimes it was easier to solve the maze if you started from the end and went back to the beginning? Yeah, it's just kind of the way our brain works. Sometimes working backward is easier to do, and it's totally valid. You can do that if you need to, if you want to, go for it. Now, with all that being said, I have to issue a warning about these methods here, these strategies. There is not a single procedure for solving problems. So keeping Polya's steps or those other strategies in mind can help, but it also might not help. And I'll explain why. What do I say here? Oh yeah, problem solving is messy, and thoughtful practice and asking why will make you a better problem solver. That's really what you have to do. Thinking about it thoughtfully and asking why. But to go back and address this issue here, one of the things that I've noticed with teaching students is that if you give them too structured of a solution strategy, then they fall victim to what happened in the first slides, right? They start realigning their mindset with defeating the problem rather than understanding it, or defeating the quiz, or defeating the homework rather than understanding the problem. And what I mean here is that you might have given them too much structure, so all they can really do now is focus on how to make that structure work the way they want it to. The example that I have is from when I was a kid and when I was teaching kids how to do this. But do you remember those mixture problems in algebra where it was like, oh, if you got a 20% acid solution and an 80% acid solution, and you wanted to make 50 gallons of a 40% acid solution, how many of each would you need? Those types of problems? Or if you don't remember those, remember the ones that were like a train leaves the station at 9:40 a.m. headed east at this speed, and then another train leaves this other station heading west and all this other stuff. And like, when will they meet? That kind of thing. Well, one way to solve those is using a table. And that was the way that I was taught when I was a kid, is to use a table. And the table looked something like this, and there were like a few rows and there were a few columns, and you had to put in some data. And I was always told that you're supposed to add across, or no, that's not what it was. It was it was the other. It was like you multiply across and then you add down, right? This kind of, so you get some result and then you add it up, and then this is supposed to be your final answer down there. So the problem with teaching students this method is that they divorce themselves from understanding the problem, and what they do is they start trying to figure out what's supposed to go in that box, what goes in that box, that box, that box. And the question is now, how do I fill in these boxes in the correct way so that I get the answer? Well, that's not solving the problem. That's not solving the problem. That's essentially being a robot. That's asking what data goes into this box to make this box spit out the correct data. Well, that doesn't mean you understand what you're doing. And at that point, you've stepped out of the realm of understanding and you've stepped into the realm of just manipulating symbols and pushing them around. The other downside to using this method to solve those problems is that the table has to change depending on what the problem is. So if the context of the problem is tweaked even a little bit, then that table no longer works and you need a different table. Or it won't be multiply anymore, it'll be add instead of that. So students end up developing this like bank of tables and trying to figure out which table to use for this problem and which entry goes into this box. That's not knowledge, right? That's not understanding the problem. That's just trying to defeat the problem. So just keep in mind that thoughtful practice and asking why is what makes people a better problem solver, makes people better problem solvers. That's what it is. You can also consider all of the SMPs here. All of these SMPs can be relevant to problem solving, making sense and persevering and solving them. You don't want to give up. We'll talk about that more later too. I think it's in the next lecture, and I'll definitely bring it up as we go along. Modeling, maybe that can help solve a problem, using the appropriate tools strategically, and so on and so on. Yeah, so that's pretty much it. Let's play. This is activity 1A. But before I show it to you, what I want to do is I want to talk a little bit about the activity rubric, just so that everybody is clear what I'm assessing with these activities. And I've got it pulled up right here. You can find the rubric on Beachboard if you need to refer to it again. It's also in these slides, and it's also right here in these lectures. So every activity is going to be worth 10 points. So if you add those all up, you get 10 points. And here are the different categories that I've split it up into. For one, your figures need to be well drawn and properly labeled. So these are all like the questions I'll be asking myself as I go through and I grade your activities. Are the figures well drawn? Are labels appropriately used and appropriate labels included? Does the figure follow the guideline examples in the slides? Because I'll do examples of almost all of these things, and your answers should be similar to mine, although they should not be identical. Not at all. And there's lots of ways to do this, but I like to give people an example of it at least, so that they have somewhere to start. So that's the first one. So 2 points for that. Notation is used correctly. Is your mathematical notation used correctly? Is the equal sign abused? We'll talk about that later on, but you don't want to abuse the equal sign. So what students like to do when they're trying to model things is they'll put everything is equals. You know, 1/3 equals 0.3 equals triangle equals my final solution. Well, that's a nonsense sentence. Doesn't make any sense. The equal sign is a very, very special sign that means these two things are the same. They might have a slightly different look, but they're numerically identical, as in this thing is the same as this thing over here. That's the only time I would use an equal sign. Only time I would ever use an equal sign. And you only want to use an equal sign when you're talking about numbers. Numbers, that's what you want to save them for. Occasionally you can use them for representations, but my general rule is just never use an equal sign unless you're specifically using it between numbers and the two things on either side are actually the same number. I'll talk about that more as we go along, and you can ask me more as we go along too. Yeah, so reasoning is communicated. You need to actually communicate your reasoning. Just throwing out an answer is not sufficient. So on some of the activities, you'll see that some of the answers, there really isn't much reasoning to show or reasoning to say, and that's fine. You can always ask if you're uncertain, but in general, you should be communicating why something is true, communicating your reasoning. Is your solution clear and well explained? Did you use complete sentences? You got to use complete sentences, right? Complete sentences. Proper punctuation. This is a big one right here. Are annotations used to communicate with the reader? So what that means is you want to keep in mind that what you're writing down on these activities, they're not just for you. It's not scratch work. You're not turning in scratch work. You're turning in carefully thought out answers that you've taken the time to write and explain. So it's not just scratch work where you're like, you know, like I roughly got the answer here and I'm just going to turn that in. No, if you do that, I'm going to have to take points off because you're supposed to be communicating with the reader. And in this case, it's me. In the future, it's going to be your fellow colleagues. It's going to be your students. It's going to be grant committees. It's going to be lots of people. You're communicating, and your communication needs to be clear. What else is, are definitions and theorems cited correctly? Is vocabulary used correctly? Here we go. We were talking about this in the previous lecture, right? If given a contextual problem, is the final answer given within this context? Look back. Wait, was that the previous lecture? No, I think that was this lecture. Is understanding of the grammar of mathematical language indicated? We'll talk about that more as the course goes on, mathematical language and grammar. Next, the solution is valid or sound and final answer is correct. So first off, is your final answer correct? Is the argument presented sound, meaning is it valid and derived from true premises? And then if the solution is not sound, meaning like let's say an error occurred somewhere, like let's say you dropped a negative sign somewhere along the way. At that point, your argument is no longer sound, but it could still be valid mostly. And I'll look for that. So for example here, if a negative sign is dropped, if I ignore just that error, is the rest of the argument mostly intact? And if I were to compare it to what would be argued if you didn't drop that sign, would it basically be the same except for that negative sign? If that's the case, then you can get partial credit for that. You can get partial credit for that. There's a difference between soundness and validity. And I'm looking for both, but just because your argument is not sound, it doesn't mean that you just get 0 points, right? And then lastly, the activity is complete. So you do need to complete the activity. Have all the problems been completed? Have you answered each question completely and fully? So that's what you should be thinking of when you do these activities. Okay, so let's take a look at activity 1A. Let me pull it up here. Activity 1A, 1 second here. Here we go. So this is activity 1A, the staircase problem. And let's first talk about these little instructions right here. You should always make sure to read these instructions, although they should be the same for each one. But we'll see. If they're not, then just make sure, just check. This is just reminding you, make sure that your sketches are clean and clear. You are not submitting scratch work. This is not scratch work that you're turning in. You're turning in the final completed solutions that are written cleanly. Your pictures need to look nice. Your models need to be drawn neatly. This is not scratch work. Use complete sentences and appropriate grammar. And yeah, here you go. What you are writing is intended to communicate clearly your reasoning. That's what you're writing down, explaining your reasoning. Lastly, you must submit your work as a group to the appropriate Beachboard Dropbox. Has to be submitted to that Dropbox. No, I don't accept any emailed solutions or anything like that, because then it just becomes, frankly, a nightmare of getting all of these different things from all these different avenues of communication. You have to upload it to that Dropbox. Yeah, it has to go to that Dropbox. I'll just leave it at that. You can find the link to that Dropbox on this activity's homepage, which you'll see on Beachboard. Okay, so that being said, let's talk about the problem itself. So the problem here says, consider the following sequence of figures. And what this is an ascending sequence of staircases of height 1, 2, 3, 4, and so on. And actually, I think I have some more info on the slides. Hold on, let me go back to the slides for just a moment here. Yeah, here we go. That's the same kind of thing. That's the same kind of thing. So let me go back. Okay, so back to this. So what we're going to do is I want you to use the Graph Square app or the Cube app on Toy Theater, which is a virtual manipulatives website, or at least it has a section for virtual manipulatives. And what we're going to use is we're going to use this to try to emulate some of the physical manipulatives that we would use in person. In particular, we're going to use the Graph Square or the Cube app to virtually emulate linking cubes. So some of you might have seen these before, and let me give you a closer look for just a minute here. Linking cubes are basically these things, right? So some of you have probably seen these before. Maybe you have them at home, maybe you played with your siblings with them. These are amazing manipulatives for kids. They're basically little cubes, and they have little sticks sticking out, right? Sorry, little sticks sticking out. And then you can link them together. That's why they're called linking cubes. You can link them together, right? And what you can do is you can make things like staircases. You can make things like staircases. I actually have a couple pre-made right here. So here's 2 staircases right here. And that's the idea. So because we cannot physically handle these ourselves unless you happen to have them at home, we need a virtual emulator, and that's what Toy Theater is. So what I'd like to do is I'd like to pull that up, and we're going to see how we can practice working on this problem using this app. So let me go to that really quick. I've got it pulled up right here. There we go. Okay. So you can link directly to this website by clicking on the link in the activity, but let's just kind of look around. What I did here is I went to Teacher Tools, as you can see right up here, Virtual Manipulatives, and then down here you have all of these options. All of these options to do all sorts of fun things. We're not going to use nearly all of these at all. We're only going to use a handful of them, to be honest. And for this one, I found that either this particular app was the easiest, the Graph Square. This is Graph Square. And I'll show you the other one in a minute. But you can make staircases with this, right? So you can just drag these little cubes out. It's usually easier if you use different colors because you can see the levels a little more clearly. But it doesn't matter if you want to use same color, that's totally fine. If you want to use different colors, you can. I'm just going to make a couple of these. There we go. So there, I made a couple staircases. And now we can see that we need 1, 2, 3, 4, 5, 6 to make a staircase of height 3. Sorry, I can't really see my mouse. I'll have to figure out how to activate that. So this is one of the apps you can use. And just see what happens if you make a staircase of height 4, height 5, height 6. How many blocks do you need? How many blocks do you need? Because that is actually the question. Let's pop back to that for just a moment. So the question was this. I guess I should have mentioned that before I cut away, huh? The question says, how many blocks you would need to build a staircase that has these heights. So basically we want to know how many blocks you need to make a staircase of height 10, 20, 50, 100, and then n for any number, any positive integer n. Like how about a staircase of height 1,000,000? How many blocks do you need? How many blocks do you need? So yeah, that's the question. And you can play around with Toy Theater to see how it goes. So let me cut back to that here. You can see how it goes. They have another app on here that you can play around with. I didn't find it to be as nice. Where is it? It's at the bottom. Oh, Cube. So Cube is actually three-dimensional. Oh yeah, see, there we go. It's actually three-dimensional, and you have some tools up here. This plus sign lets you add a cube. The hammer lets you break cubes off. There you go. I think this lets you zoom in. This lets you grab and turn things. There you go. So if you really, really wanted to emulate the actual three-dimensional staircases, you can try to do it using this. You can change the color if you want. I think you can actually like select colors. Let's see. There we go. So now if I make a new cube, there we go. It's going to be brown. One thing I noticed that's a little bit difficult about this particular app is that you have to click, quote unquote, on another cube to get it to work. I'll show you what I mean. So if I click away, like I don't actually click on this little shelf thing that I've made, the cube won't appear. But if I click here, a cube will appear, right? And I can add more. See, now I'm trying to click above, but it's not letting me make a cube. I have to actually touch the previous cubes to get it to appear. So there you go. I made a staircase of height 4, and now I can look and see what's going on. Huh, interesting. So yeah, it looks like it's changing the color when I click on it to move it also. So it's a little bit, I see it's a little bit glitchy, but you get the idea. And this is actually why I was saying at the end of the previous lecture, these are things that you should consider as a future educator. Is this website that great? Is there a better website? Is there another website? Is it free? Think about, is it easy for you to use? Is it easy for children to use? These are all things that you should consider. And so if you want, you can explore that in this course. Anyway, so you can use either of those two apps to work on this particular activity. And I want to see at least a couple staircases made with these apps on here. And then you should actually have your answer and your reasoning. So let me cut back here. Yeah, so in the end, the question is this that I've highlighted. How many cubes does it need, or how many blocks do you need to make staircases of those different heights? And notice that in the end, you have to find a staircase of height n. So that means that you're going to have a formula at some point, and you have to derive that formula. And then we're going to talk about where that formula comes from. That's the key idea, but that'll be the next lecture. Okay. Oh yeah, there's a nice little hint down here. So think about that. Think about maybe trying 2 staircases. And also, do not use brute force calculation. What I mean is, if you're trying to find how many cubes are in a staircase of height 100, the goal here is not for you to literally hand grind through and calculate how many it's going to take. That's not the goal of this activity. All right? Okay, so let me cut back here. Let's see, on the slides. The staircase problem, and that's it. That's it. Okay, so that's it for lecture 1A. At this point, you can stop, and then I'll see you in the collaboration meeting to do activity 1A. All right, have a good one.